Okay, in this lecture I want to discuss scaling and prototype circuits. So we'll get right to the next slide and then I'll give you a little more information on what scaling is. So first of all, let's talk about what a prototype circuit is. So a prototype circuit has a few things that we do or try to do. First of all, a prototype circuit is going to have a cutoff frequency of 1 radian per second, and this is pretty consistent. And the other thing that's pretty consistent is it has a gain of 1. Now, what's not always consistent, but certainly for the filters that we have looked at so far work, and that is to have the resistor and capacitor values set to 1 whenever possible. It's this little whenever possible statement that implies that there are some exceptions, and there are. Specifically, the filter that we will cover this semester where we cannot initially set resistor and capacitor values to 1 is the Butterworth filter, because their values are specified by other relationships. However, for what you have seen so far, for example, the prototype low pass, we set the resistor equal to 1 ohm, the capacitor equal to 1 farad. That's going to give us a cutoff frequency of 1 radian per second. We set both the input and the feedback resistor equal to 1 so that we have a gain of 1. Same is true of the prototype high pass. We set the resistors equal to 1, the capacitors equal to 1, giving us a cutoff frequency of 1 radian per second. So the reason to do this is because as we get to more advanced filters, well, two things. First of all, let's suppose that you have a filter designed for a specific value of capacitor, and then you find out for whatever reason that capacitor isn't available or won't work, and so you need to use a different value. If you have designed your filter based on a prototype, then we can use something called scaling that allows us to keep our cutoff frequency the same or adjust the cutoff frequency or adjust the values of the resistors and capacitors. So that is why you're motivated to design around a prototype. The other thing is using a prototype filter allows us to do things like compare apples with apples. So for example, let's suppose we want to compare a Butterworth filter with some other type of filter. If we design both to be a prototype, meaning a cutoff frequency of 1 radian per second and a gain of 1, then what we can do is we can basically model both filters and see what the differences are for the same cutoff frequency. So anyway, that is what motivates us to work with prototype circuits and then to scale from that. Now, typically, the thing that you work with first is the cutoff frequency. So if you're given a prototype filter, you know you have a cutoff frequency of 1, but in design specifications, you'll be told the cutoff frequency that you want to have. So you may be told you want your cutoff frequency to be 1,000 hertz. So first we would convert hertz to radians per second, and then that would give us the cutoff frequency that we would have to use. So typically that's the scaling that you want to do first. So let's talk about scaling. So as we said, when designing and analyzing filter circuits, it's convenient to use component values like 1 ohm, 1 henry, 1 farad, and so on. First of all, because calculations are simple, and secondly, because it's an easy way to compare across different types of filters. Now, unfortunately, as you know, those are unrealistic values for those components, and so we don't really want a filter with a cutoff frequency of 1 radian per second, nor can we purchase a 1 farad capacitor. However, what we can do is if we design around these convenient component values, we can then use scaling to transform the undesirable filter characteristics into desirable ones and the convenient component values into realistic ones that we can purchase. So having said that, there are two types of scaling: magnitude scaling and frequency scaling. Magnitude scaling is done when you need to change the value of a component in a circuit. So if you can't buy a 1 farad capacitor, what can you buy? Let's suppose you can only buy a 100 nanofarad capacitor. So what magnitude scaling allows you to do is it allows you to determine what the other values of elements in the circuit need to be in order for you to have the same frequency response, but use the components that are specified or available. Frequency scaling means you're not going to change how the filter performs or the shape of the frequency response, but you might want to change the cutoff. So in other words, you might want to move your cutoff frequency from 1 radian per second to some other value that's been specified. This means basically that the impedance of each circuit's component in the scaled circuit needs to be the same as it was in the original circuit in order to keep the frequency response the same. So let's look specifically at what we mean by this. So basically, we scale the circuit in magnitude by multiplying the impedance at a given frequency by the scaling factor K sub m, which is known as the magnitude scaling factor. Now, resistors and inductors will be multiplied by K sub m. Capacitors are multiplied by 1 over K sub m. So in this equation down here, we've let the unprimed variables represent our initial value of the capacitance, inductance, and resistance. And note that we're including inductance here because scaling can be used on an RLC passive filter as well. We just are introducing it here. So we won't really talk about any situations where we have an inductor that we scale, but just note that we could scale an inductor as well. Okay, so the primed variables represent the scaled values of the variables. So basically you have C prime is C over the magnitude scaling factor. R prime is R times the magnitude scaling factor. So let's think about this realistically. Let's suppose in our system that we had a capacitor that we could use that was 10 microfarads. Then what we would do is we would say C prime, our desired capacitor value is 100 or 10 microfarads, and C is 1 farad. And so we would then solve for K sub m. Now what that does is it fixes R. Because once we've solved for K sub m and we have our original R, our R prime is now a calculated value. So typically it is the capacitor value that sets the magnitude scale. Not always, but typically it is. Notice too, the cutoff frequency of an RC filter is 1 over RC. So if we use 1 over R prime C prime, notice the K sub m's will cancel out. And so we'll have the same cutoff frequency that we would have with our original values, because one of the magnitude scaling factor for the resistors in the numerator, for the capacitor is in the denominator. So if we're doing only magnitude scaling, the frequencies, the cutoff frequencies, will not be shifted. Okay, so suppose that we discover that 10 nanofarad capacitors, if we were looking at that, are no longer available to construct a filter that we designed, and we have to use a 200 picofarad capacitor instead. Basically, that's an example of magnitude scaling also, where 10 nanofarads would be your original capacitor value and 200 picofarads would be your new capacitor value. So you could scale everything around this new capacitor component that you're going to use instead of your original without having to change how the filter responds in the frequency domain. So that's magnitude scaling. Now, frequency scaling, we scale a change in frequency by changing the circuit's component values so that at the new frequency, the impedance of each element is the same as what it was at the original frequency. Because resistive impedance is independent of frequency, resistors are not affected by frequency scaling. So if we let K subscript F denote the frequency scale factor, inductors and capacitors are both multiplied by 1 over Kf. Hence, the frequency scaling factor is found by taking the desired frequency and dividing it by the prototype frequency. Since our prototype frequencies are typically 1 radian per second, then the frequency scaling factor is the new or desired frequency in radians per second. Now, typically frequency specifications are given in hertz, so to solve most problems that are specified by a customer, we would need to convert that to radians per second first. All right, well, it turns out that usually you want to do both frequency and magnitude scaling, And so these can be combined. And if you here's just a summary of magnitude scaling, a summary of frequency scaling. And over here's what happens if we combine the two types. So combining the two types, our new resistor value would be our magnitude scaling factor times our old resistor value. Our new capacitor value would be our old capacitor value divided by the product of the magnitude and frequency scale factors. And the new inductor value, if we were working with inductors, the new inductor value would be Km over Kf times the old inductor value. And notice here that this set of notes that I've modified needs an L here after the Km over Kf for the original inductor value. The slide that was provided here actually would not allow me to modify the equation. So just put an L in there when you're looking at the notes. All right, so just to review a little bit, this is a prototype low-pass filter. What is its cutoff frequency? You can easily see here's our RC that's going to impact the cutoff. And so omega naught is 1 over RC, so omega naught here is 1 radian per second. Here we can use both magnitude and frequency scaling to create any desired low-pass filter from this prototype. What should the frequency scale factor be if we want a cutoff frequency of 5 kilohertz? So if we want a cutoff frequency of 5 kilohertz, that's 5 kilohertz times 2 pi radians per second, or 10 pi kilohertz, or 10,000 pi, which is answer A. So A is the correct answer here. Okay, finally, what component values change as a result of frequency scaling? So all the components, just the resistors, or just the capacitors? So you may remember a couple of slides back we talked about for frequency scaling, only the capacitor values will change because the resistor and the value of resistance is not a function of frequency. Okay, now let's talk about a magnitude scaling factor. So here's our prototype filter. Suppose we wanted to use 1 kilo ohm resistors. What magnitude scale factor should we use? So let's go back and find the relationship for the resistor. Here's the new resistor value, here's the old resistor value, and here's the magnitude scaling factor. So R prime is K sub M times R. So now going forward to the one we're looking at, if we want to use 1,000 ohms, that would be our R prime. Our R would be 1, and so in order to get that kind of factor, we would have to scale by a factor of 1,000. So the correct answer here would be C. Okay, and finally, which component values change as a result of magnitude scaling? All of the components change as a result of magnitude scaling.